Uh, so a couple of housekeeping things to start. We need to set up our new OneNote notebook. Um, so to do that, you want to go into Microsoft Teams. So if you go to the search bar at the bottom and do Teams, you want to make sure you pick the work or school one. You should see a tile for first hour calculus. I set this up yesterday, so everybody should be preloaded in there. If you're not, holler at me. Once you find your first hour AP calculus tile, go ahead and click on that. On the navigation panel here on the left, you'll pick class notebook. Yeah. And then the Teams updated or whatever, so it's a little bit different. Once you've clicked on class notebook, over here there's like this little button that says editing. From the drop down, you'll just want to pick open in desktop app, and that'll load in the new notebook into your OneNote. So go ahead and take care of that now. I've closed out my notebook from last semester. So if there's stuff in your notebook that you're going to want, what I would do, or what I would recommend, is to move that content into a non-shared OneNote location and then close out last semester's notebook so you don't end up with like some silly sync issue where it's trying to sync a notebook that's not open anymore. But for the record, I went and still like put in, like I still have all of the, everything from last semester in here still. So it's all still there in your new notebook. I just moved what I had for, I can't remember if I used second hours or fourth hours or whatever. I picked one of the periods and just moved that stuff over. But if you had specific things, like if you had homework or whatever that you wanted to hang on to, I would suggest moving those out of your shared folder into a non-shared location and then closing out last semester's shared folder so you don't run into any weird sync issues. Does everybody feel okay doing all those tasks that I just kind of talked about? I think at this point you guys have had me enough times and done enough here on OneNote that you should feel okay doing those things. If you're not, holler at me and I'd be happy to assist. How's your vacations?
Short.
It does feel short, doesn't it? I would have rather gone that full week of before Christmas and then had the rest of this week. Yeah. I would like a little bit, like once you get past Christmas, I feel like I can finally like relax a little bit. But those days before Christmas are not very restful to me. But that's just me. I'm not going to talk about the syllabus at all because it's literally the same syllabus as first semester. Class will be set up the same way. We'll go back to doing some of the, like the partner homework stuff beforehand. Some of that will be mixed in, just like review stuff from first semester and not necessarily all just last night's homework. So as we're getting further and further away from some of these first semester things, I want to kind of keep that stuff present. So it's still fresh when we get to exam time here in the spring. So not always will the little homework assignment at the start of class be just a problem from the previous night's homework. It might be something from first semester still. So just as a warning on that, I haven't sat down and done anything with it yet. But I do anticipate doing some more of that so that we're still kind of keeping those things fresh. Everybody okay with that? Hopefully that leaves us in a little better preparation place in the spring come exam time. If we're kind of not letting any of that stuff get too far away. All right. So the plan here, we have two little hanging sections that I wanted to do first semester that we didn't get to, and then we'll be starting what would be called integral calculus, the bulk of second semester. So we're going to cover all of chapters 4 and 5, and then we'll do little bits of stuff from 6, 9, 7, and 8, time depending. There will be a few topics that I want to do that I think are important to do, particularly if you're planning on taking a college calculus class, that are BC topics and not specifically AB topics. So we will do some of that stuff here this semester also. I'll make sure I announce that beforehand, and we'll talk about like what you would be responsible for as an AB test taker versus a BC test taker. Everybody feel good? All right, well, let's get into it here. So we're going to start by talking about Newton's method. So you guys know how on your graphing calculator, when you go in, you do the zero function on the graph, and the graph can find the places where you cross the x-intercept or cross the x-axis, right? The way the calculator is doing that, now I suspect, I don't know, I haven't dug into the specific programming, but my suspicion is the way that the calculator is doing that is some version of this Newton's methods technique that we're looking at here. So really what this is a way to approximate a solution to a polynomial, or really any kind of equation, but most often we'd apply this to like a polynomial situation. Because if you remember back from Algebra 2, solving a polynomial is not trivial, right? If you have a big degree polynomial, that can be quite time consuming. And if there are no rational solutions to start with, and it's not like in a specific like form, finding the irrational solution there's nothing really we have. There's like no good tool to use to do this, right? So what we're looking at here with Newton's method is just a way to make a sequence of linear approximations to estimate the value of a function. Most often that estimate, the value of the function we're looking for is 0, right? It's essentially a method to solve an equation. So if we take a look at the picture here, what we're doing, or what this is kind of describing to you visually, is what this Newton's method is. So what we do is we pick, okay, stop please, is we pick some point on our function. We then write the equation for the line tangent to the function at that point, which we know how to do, right? We've done that a bunch of times. And then we find the x-intercept for that tangent line. We then plug that x-intercept into our function and get a new point on that function. We then write a new tangent line. So the line tangent to that function, or to the function at that point, we find its x-intercept. We plug that x-intercept into f, and we continue this sequence, and ideally, we end up with the actual x-intercept for our function. That's how it's supposed to work. So the formula here that we'll use is that next point, the we call that next point x sub n plus 1, is the previous x value minus f of that previous x value divided by the derivative evaluated at that previous x value. So to show you where this formula comes from, let's just take a look at starting here. So let's say we pick the point x1 comma f of x1. So that's our first point. And what we're looking to do is find this next value, x2. So to find that, we write our equation for the tangent line at x1. So y minus y1 equals the slope right? That's just our equation for our tangent line. Which is that. If we're looking for the x-intercept, the y-coordinate becomes 0. And now I'm solving for x, right? So I'm solving for x. So I'm going to add over that piece, add over this piece. Yes, Jacob.
Can you transfer over the negative after that's 1? Why is it still negative?
Oh, thank you. Yep. Thank you. Thank you. Yes. Great. So far, so good. And if I divide both sides then by the derivative evaluated at x1, it's going to cancel here. But I'm still going to have it divided over here. And if I just call that x2, which is what we just found, that's our derivation, right? So if this is n plus 1, that's n. And we have now the formula we've just given you. That's just me deriving that formula. Yes, like a proof. Just showing you where the formula comes from, that it's doing exactly what we just described, right? When I gave you the outline of like what we're doing, it's just me showing you algebraically how we did it. Okay? Now notice that if the solution if f of r is equal to 0, if I do this Newton's method infinitely many times, that x-intercept should approximate or should approach r, right? The actual solution. Everybody's okay with that? Yeah, so if the actual x-intercept here is r, the more times I do Newton's method, the closer and closer I should be getting to r. If I do that infinitely many times, I should actually get to r, right? Very normal calculus idea, right? How do I get there? Well, I just have to do this thing infinitely many times, right? Get infinitely close to it. Sure. Now, will Newton's method always work? No, right? It's going to be highly dependent on your choice of that very first point. So let's take a look at an example of where this goes bad. So here we've chosen this point x1. We do our x-intercept. So there's our new tangent line. It goes over here. And that's going to come up there. So it's just like you're just kind of dancing around, not actually getting anywhere closer, right? So one thing to be cautious about is that this isn't necessarily going to always work. Okay? That's the downside. In your calculator, when you do this x-intercept command, what's the first thing the calculator asks you to do? It asks you to give it a left bound and a right bound, right? So what it's basically doing is saying, instead of this function being infinite in either direction, it's now a finitely long function. So if it sends me off past the left bound, I just use the left bound as my x. And if I go past the right bound, it just says use the right bound as your x. So what it does is it keeps something like this from happening on your calculator by doing that. Now, would I expect you to make that accommodation here when we're doing this by hand? Definitely not. But I wanted to point out to you, like, Mr. Kulik, when I do it on my calculator, I never get, like, it always comes up with an x-intercept. If there's an x-intercept there, like, it finds it. Why does it work there? And the reason is because the calculator needs your input on saying, okay, somewhere between here and here, there's an x-intercept. Good. Now I can, if I go outside of that range, I know I can just, like, cut off and just pick the point at the end of the range rather than having to continue on forever, getting further and further away from R. Okay. So let's do this as an example. Take out let's do this by hand first. Okay. So the two things I need to do this, I need my f of x and I need my f prime of x. Quick, what's the derivative? 3x squared minus 2. Okay. So x1 is 2. x2 is going to be x1 minus f of x1 divided by f prime of x1. So that's going to be 2 minus, and then what is f of 2 going to be? Well, that's 8 minus 4 minus 5, so that's negative 1, over it's 12 minus 2 is 10. So that's going to be 2 plus 1/10, or 21/10. Everybody's okay? So then the third approximation, x3, should be x2 minus f of x2 over f prime of x2 and then this is calculator time, right? Because I'm not about to try to plug through 21/10 into the squaring and cubing. Like, get out of here. That's not worth my time. Let's show you guys how to do this on our calculator in a nice, efficient way. So pull out your graphing calculator for me. Press the y equals menu. Into y1, we're going to type our function f. Into y2, we're going to type our derivative, f prime. Everybody, so far so good. Okay, I'm going to exit out of here. I'm going to type in my first approximation and press enter. And I'm going to do ants minus, and I'm going to do alpha y equals and pick the first fraction command. And I'm going to do y1 of, so I'm going to do vars, y vars, function, y1 of ants divided by, I'm going to do vars, y vars, function, y2 of ants so this is just the formula, right? Is everybody okay so far? Elena, what's up? Oh, second and the negative sign gives you the ants option. If you notice below, above the negative sign is blue ants. That is the previous thing. So I'm going to press enter. There's my 21/10. Guess what happens if I press enter again? It gives me the next approximation because of the way I've set this up. I don't have to keep typing it in over and over and over again. If I want the fourth approximation, just press enter again. And I can just keep pressing this and pressing this over and over again. And I'm getting a new approximation every time, which is really cool. And here's the best part, right? Let's say maybe we wanted to, instead of starting with x1 at 2, what if we wanted to start at 3? So all I need to do is press 3 and enter. And if I do second and enter twice, it'll recall that thing that I just typed in. So there's no update needed from me. And I can just like grind through that again with a couple of enters, and I'm like back to doing the same thing, which is really nice. Like, how lovely, lovely, lovely does that? Isabel. So you have to press the vars button and then go to y vars and then pick function from the list. Did you find it? Yeah, it's kind of below the down arrow. Well, because the formula is a recursive formula. It's just saying, take your previous answer and then plug that into this formula. And you get a new answer. And then it says, take that answer and plug it into the formula. And it says, take that answer and then plug it into the formula. So because the way we set it up on our calculator, where it's like, just taking the previous answer from the calculator and it plugs into the formula. That's why we can get away with just pressing enter each time, because just taking, because we use this ants in there, it's saying take the previous answer and then plugging into the formula. Is that? Which is really slick, right? That really saves you a ton of time in typing stuff in your calculator. Tessa. Yes. What is that telling you?
Intercept.
That's probably because that's the intercept, right? So, if the limit is x goes to infinity should get you to r. Well, we've gotten, if it's not changing anymore, what do you think you've done? You've just gotten to r. It just happened really quick. Instead of needing like infinitely many iterations, you got it after 2 or 3 or 4 or 5 or whatever. Which for a fairly well-behaved function is not surprising. All right. What if we say use Newton's method to find the 6th root of 2 correct to 8 decimal places? So what is this formula we're really looking at? Oops. It's like that, right? But that's not the way I would think about it. I would think about it as taking the 6th root of both sides. And then I'm moving everything onto one side. And that's my f. So what's f prime got to be then? Good. Okay. So I'm going to go in and change that to x to the 6th minus 2. And then 6x to the 5th into y2. Everybody feel good so far? We need a guess. I'm going to just make my guess 1. Because I know that the 6th root of 2 has to be somewhere between 0 and 2. Just pick 1, seems like a good guess. And if I do second and enter twice, it gives me that formula that we typed in earlier. Notice I didn't have to retype it in again. And now I'm just going to press enter. Ooh, you know what? I want, well, maybe if I just press this enough times, it'll give me a decimal. Let me think here. It did?
Yeah.
Okay. It eventually gives you, okay, great. So what I'm going to do now, it says it wants it correct to 8 decimal places. So if I press this again, I notice I'm correct to 2 decimal places, right? Because 1.12 is the same. So we have 2 decimal places that agree. Press it again. Now I'm correct to 4 decimal places, right? Because I have 1.1124 is the same on both of them. And now I'm correct out to 7 decimal places. If I press it again, now I'm correct out past 8. Does everybody feel okay as to like what I did there? What's the lovely part about this? It's the calculator doing like all of the hard work for you, right? Like this is the beautiful, beautiful thing about this, especially with your graphing calculator, that you're able to kind of do like these iterative operations where it's just like all I have to do is set it up and just press enter until I get what I want. Yes, we like that. Yeah, go ahead.
Could you just plug in like a 6th root of 2 that when you're typing it in the chat?
Sure.
Right, and it's going to give
Yeah, we're operating under the under the notion of you're pretending you're Isaac Newton, and you don't have a calculator that can give you a decimal approximation of this. How are you going to get the value, a good approximation for this, right? And really, your calculator even is not even giving you the exact value of the square or cube or sixth root of 2. If you take like calc 2, you're going to learn how the calculator is actually doing this. And what it's doing is it's constructing a polynomial that gives you a decimal approximation that's accurate within like X number of decimal places, whatever the programmer's programmed in. It's not actually calculating the sixth root of 2. It's just using a really accurate polynomial approximation of it. Just like it doesn't actually compute sine or cosine or the logarithms. All it's doing is using a polynomial approximation. And it's building that polynomial approximation using techniques that you'd see in a Calc 2 course, or even if you took the BC calculus course, you do a little bit of that there. So you're doing it building like a Taylor series or a Maclaurin series, and those words mean nothing to you now, but that's actually what the calculator is doing, is it's just creating a really accurate approximation. But this is another way of doing that without doing nearly as much calculus. This is a much simpler way of doing it because all you're doing here is a derivative, not that difficult, and then like addition and subtraction and division iteratively, which is a pain, but like definitely doable for somebody in the 1700s, right? Like nothing here required technology or like a terrible geometric construction to get like the sixth root of something where it's like I'm drawing, like I'm doing some careful pencil and paper construction with a compass and a straight edge to kind of come up with the sixth root of like, this was fast in comparison. So our last example here says find, correct to 6 decimal places, the root of the equation cosine x is equal to x. So what should our f of x be in this case? Cosine x minus x, right? You just get it onto one side so it's equal to 0. And then our derivative is going to be, excellent, negative sine x minus 1. And what do you suppose we should pick as our first guess? Well, I would just pick 1. To be honest, a 0 would concern me of getting like something that I don't want. I don't know. 0 seems like a poor guess, but all right, let's go ahead and so we have to update our y1 and y2. Maybe 0 would be fine. I don't know. I try to stay away from 0. Weird things happen at 0, But it might be fine. I really don't know. And now I'm annoyed that I have this stupid fifth root or fifth power floating around. There we go. All right. Reset that to 1. And second and enter twice. So I'm 1 decimal place is secure. Oh, that got me 3 decimal places already. And that gets me past 6, so I'm happy there. What are you guys noticing here with this assignment? Yeah, not a lot to do, right, by hand. The calculator is going to do most of the work for you, which is really nice, right? It's just about being literate with our calculator and being able to set this up in a clever way where all I have to do is press enter a bunch of times and like, got it. And as you can see from the homework, I didn't ask you to do a whole lot here. Handful of questions. How much time do we have? 3 minutes sounds like a good place to stop. Look at that timing. Pretty good for the first day. Rita, yeah, go ahead.
So after you typed in the 1, then you press enter.
Mhm.
Like, so you press like second and
Yeah, if you press second and enter, it's going to give you the last thing you typed in. If you press it again, it'll give you the second to last thing you typed in. If you press it again, it'll give you the third to last thing you typed in. Alternatively, you can always like go with your arrow up, highlight it, and just press enter, and it'll give you that same thing again. So either way of doing it, you're going to get to the same spot. Jacob.
It doesn't really matter what number you start with, right? It's just how many times it's going to take.
Well, I think sometimes you can get like things to diverge where it just might overflow your calculator before it comes back. So you have to be a little bit careful, but if things aren't looking like they're going the right way, just maybe start with a different value. I think if you use 1 more often than not, you're going to be okay.
Okay. Because if you pick a number like below the intercept, it'll like mess you up, right?
Not necessarily, but possibly.
Okay.
And I think on the homework it asks you to try, I think I have a question in here where it's like, hey, try this one and then try that one and see what happens.
On the first one we did, I started with like 12.
Yeah.
Took more, but I got there.
Yeah. And again, if you have like a pretty smooth polynomial, it's probably going to work out. But like, I don't want to say that every time, because if you have like some weird piecewise, like, like you have to think about, the weird stuff before I answer like an always question. And that's one where it's like, am I guaranteed that this is always going to iterate eventually to the end?
Does it need to be a continuous function too?
It does not.
It just has to be differentiable.
Yes.
women accept.
Well, no, it just it should be differentiable over the domain.
Right.
But like, obviously, if
Outside the interval.
yeah, the place where you get into trouble would be like if you had an absolute value function whose the solution is like the point is on the x-axis, and you're trying to find that using this. I don't think that'll work.
Okay.
Right?
Thank you.
You're welcome. Have a good
Thank you.
one. Bye. Have some.
Tomorrow.
We'll see ya.